That's what a differential equation does. It involves the equation, function y, and is one of its derivatives. For example, y prime equals xy. Y double prime plus 2y prime plus y equals 0. The difference among these equations and ones previously encountered by us, or most of the ones previously encountered by us, is we not only have y in this equation, we have y prime. We've got a y along with one of its derivatives. And in this case, two of its derivatives. Second derivative. So that's what a differential equation does. It relates the y and essentially its derivative or one or more of its derivatives. Now we refer to order of a differential equation. The order of a differential equation is just the highest derivative that occurs. So, what's the order of the first one? This is order 1. What's the order of the second one? Order 2, because I've got a second derivative, okay? And so that's how sometimes the differential equations are distinguished by their order. Okay? First order or second order, order 1, order 2. Just FYI there. Now, what do you think it's going to take for a solution, for me to have a solution to a differential equation? Well, I'm going to have to find a y, if I'm talking about the solution in terms of y, I'm going to have to find a y that works in this along with its derivative, right, for this one. And in this case, I'd have to find a y equation, function, that would work with its derivative and second derivative. That's what you've got to look for. Or we've got to find. And the way that we'll approach these first ones, we're just going to check solutions to see if a solution is a solution or not. It's basically kind of like a proof, just show that this side equals that side. All right, so here's what we're going to do next. Verify that for the differential equation y equals e to the minus x plus e to the minus 3 halves x, verify that for that equation, that's my solution. Verify that this, forget the 4, verify that, read my own writing here, is a solution of the differential equation 2y prime plus 3y equals e to the minus x. So in other words, for this to be a solution, it's got to work in this differential equation, right? It's the function and its derivative. Plug those in, and just so that's all we're going to do for these. Just to see how these solutions do work. All right, so to verify this, like I said, we're just basically going to see, well, in this case, it's going to work out. If I plug in my y and my y prime, does it equal e to the minus x? Does it simplify out to be e to the minus x? That's what I basically need to do here, right? What's my y prime here? Well, it would be e to the minus x times minus 1, chain rule, plus e to the minus 2x, e to the minus 3 halves x times minus 3 halves. Right, because the derivative of e to something is the e to the something times the derivative of the power. Clean that up. That's minus e to the minus x minus 3 halves e to the minus 3 halves So let's take this for y, this for y prime, and see if it all works out. So I'm going to do 2 times y prime. So 2 times that. Plus 3 times that. And we're going to see if that does indeed equal e to the minus x. So it looks like a lot of things are going to have to cancel out for that to happen. All right, so if I multiply by 2 here, that would be minus 2 e to the minus x. 2 times that would be minus 3 e to the minus 3 halves x. 3 times that would be 3 to the e to the minus x, 3 plus 3 e to the minus 3 halves x. Ooh, good news. What happens? Well, this 3 e to the minus 3 halves x cancel with that positive 3 e to the minus 3 halves x. Then I've got these like terms, and sure enough, minus 2 e to the minus x plus 3, that does give me e to the minus x. So, okay, so there are such a things that works out. And usually on solutions, that's what's going to happen. So, now, next point is these solutions actually a lot of times come in a family of solutions. We get families involved here. This actually, we might say, is a particular one. Here, let me show you what a family of function solution looks like. So solutions can come in families. For example, this could be a potential solution. Y equals 1 plus c e to the x over 1 minus c e to the x. See, that's a family? Because what does c you think is? C is some constant. And basically what we're saying is c can be any number. So if I plug in any number for c there, that's going to be if this was our solution to our differential equation, that's saying that would work in our differential equation. And so we have, how many solutions is that? Basically infinitely many, right? Because y equals 1 plus 5 e to the x over 1 minus 5 e to the x would be a solution. Y equals 1 minus 10 e to the x, 1 minus 10 e to the x would be another solution. So plug in any c you want to, it's a solution. Okay, any number. That's what we're saying. And it turns out, okay, y, I got the, I didn't think I had the differential equation here, but I've got it. Y equals 1 plus c e to the x over 1 minus, are the solutions to y prime equals 1/2 y squared minus 1 in parentheses. That differential equation. This whole family here, that's the solutions to that. So there's infinitely many solutions to that differential equations. Plug in 5 for c, plug in 4 for c, you get a different solution each time, but it's obviously related, as you can see there. Okay? Now, let's show that this is true. Let's verify this. So how would I verify it? Well, I need to plug in y and its derivative. So what's the derivative here? What rule? A little bit of quotient rule? Quotient rule. I better move that there. All right, so low, 1 minus c e to the x, d of the high. What's the d of the high? C e to the x. Plus, minus high 1 plus c e to the x times d to the low, which would be minus c e to the x. Just got it on there. Okay. Write that here so you can see it on the screen. And then all over low squared. Well, that looks like a big mess, but I think it'll work out pretty nicely. That's c e to the x minus, what, c squared e to the 2x. And then that would be minus and minus make a plus, so that would be c e to the x. C squared e to the 2x is what you get. Multiply that out over 1 minus c e to the x squared. Does clean up a bit because that and that cancels, so I have 2, y prime is 2c e to the x, so we've got 2 of them, over 1 minus c e to the x squared. So I'm going to plug that in to for y prime. Okay, so y prime is 2c e to the x, 1 minus c e to the x squared. And that should equal 1/2 y squared, so I'm going to square that. And then minus 1 that. Huh? It's obvious that equals. Oh, well, you're pretty good if you can see that you equal. Oh, you're good at saying that it is? It's not too bad. You wind up having to square a little bit of stuff. Basically what we're going to do here is kind of like we were doing. This, not much you can do with that. Not much you can do with that. What we can do with this, 1/2, I guess we could multiply both sides by 2, but let's just do this. Let's make those both, square both of those. And then it's just really combining those fractions, common denominator. So if we get a common denominator there, I'll have 1 plus c e to the x squared. And then I'd multiply this one by 1 minus e to the x, c e to the x squared, top and bottom. And that would give me my denominator, which is looking pretty good because that is the denominator over here, isn't it? So that's at least one good fact there. Yeah, if I square this out, and square that out, and do the minus thing, I get 1/2, it'd be 1 plus, so 1 plus c e to the x times 1 plus c e to the x. So it's 1 plus c e to the x, c e to the x, c squared e to the 2x. So I've got 2c to the x. So it's 1 plus 2c e to the x plus c squared e to the 2x. And then I've got minus, well, 1 minus c e to the x. Everything's the same except these are minuses, so that would be minus 2. So it's 1 minus 2c e to the x plus c squared e to the 2x. And so, sure enough, it does work because, I'm not going to rewrite it. This is, change all these signs. This is plus, this is minus, this is plus. That's minus. What happens? 1's gone. 2c, oh, I've got 4 of those, don't I? Because 2 plus 2. So I do have 4. So I have 1/2. Top is going to be 4c e to the 2x, because that and that makes 4. And then the minus the c squared plus the c squared, those cancel. Cancel out the 2 into the 4. Gives me 2c e to the 2x. Aha. 1 minus c e to the x squared. Aha. We're good. Check, check. All right. But you can see there, yeah, the solutions to these are not necessarily the nicest of solutions. But all right, now, another kind of introductory bit here, and that is if we actually assign what's known as an initial condition, if we have an initial condition, then what that leads me to is a particular solution. In other words, if I have an initial condition on this function here, say if x is 2, y is 3, if I know that also, if I know that other little bit of information, then that restricts the particular solution I want. It will restrict, for example, if I know that when I start, x is 0, the y value is 3. Sometimes we do know that, right? Like the height, like on the height function, I know I'm starting at height 3 or 100, whatever. That's what we're talking about, initial condition. So if I start with an initial condition, then I can find a particular solution. That's what we're going to do here next. Okay, here's the statement. Find the solution to the differential equation, same one we just had, y prime equals 1/2 y minus 1, from our family y equals 1 plus c e to the x over 1 minus c e to the x, that has the initial condition, initial value, y, and this is the way they'll approach it, y of 0 equals 2. So what this amounts to is, with these values, I want to find this one, the one particular solution or whatever, the particular solutions that works in this case. In other words, what it amounts to, I want to find the c value here. What is c if this is our initial condition? We usually don't do y of 0, but it's similar to the f function notation, isn't it? What does that mean, y0 equals 2? Well, doesn't that mean what's the 0? That's the x value. And then the 2 is the actual y, right? It's function notation. The parentheses have the input value, which is the x value here. And so to get what they want here, that's what I'm going to do. I'm going to plug in x to be 0, y to be 2. Right? And x is 0 works out well because what have we got? E to the 0, that's 1. That's 1, so I have 2 equals 1 plus c over 1 minus c, don't I? I just have to solve that for c. Multiply both sides by 1 minus c. Because that'll cancel the 1 minus c's out. So I have 2 minus 2c equals 1 plus c. Get c on the side by itself. It's looking like a 1/3 or something like that. Subtract c and subtract 2. What do I get? So minus 3c equals negative 1. Divide by negative 3. Yeah, c is 1/3. But that's not really the answer. The answer is find the solution, the particular solution with this initial value. So that would mean plugging in our c value right here. These are the family of solutions. So I need to plug in my c value. So the solution they want is y equals 1 plus 1/3 e to the x over 1 minus 1/3 e to the x. All right? Not too bad, right? Okay. Well, the question then becomes,